Hi students, good morning. Our today's point is principles of perpendicular axes or principle of perpendicular axes. So write down the question first. State state and prove state and prove principle, not principles, principle of perpendicular axes. This is our today's question. This question is important, so denote it as VVIMP. Our previous principle is principle of parallel axes, but it is for three-dimensional body like this. But if the body is a plane sheet called as a lamina, then the principle of perpendicular axis is used. Now suppose that this is a lamina, if it is rotating about an axis like this, rotating about an axis perpendicular to its plane, that means this axis, then its moment of inertia about an axis perpendicular to its plane is equal to sum of its moment of inertia, means moment of inertia of lamina is equal to the sum of two mutually perpendicular axes in the plane of lamina. Suppose that this is x-axis, this is y-axis, these are mutually perpendicular and in the plane of the lamina. So repeat this explanation, listen it carefully. The moment of inertia of a plane lamina, if it is rotating about an axis perpendicular to its plane, means this, is equal to sum of its moment of inertia about two mutually perpendicular axes in the plane of the lamina intersecting at a point where perpendicular cuts the lamina. That means when perpendicular is at this point, then the point of intersection of x and y axis should be here. If it is perpendicular axis is here, then x and y axis intersect at a point where the perpendicular cuts the lamina. So I would like to repeat the statement again, and it is the moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to sum of its moment of inertia about two mutually perpendicular axes in the plane of the lamina intersecting at a point where perpendicular cuts the lamina. So write down this statement. This is our statement. 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 The moment of inertia of a plane lamina of a plane lamina plane lamina about an axis perpendicular about an axis perpendicular to its plane, to the plane of lamina is equal to the sum of its moment of inertia is equal to the sum of its moment of inertia about 2 TW, about 2 mutually perpendicular axes about 2 mutually perpendicular axes in the plane of lamina intersecting at a point where perpendicular cuts the lamina, where perpendicular cuts the lamina, Proof. Sorry. This is a theoretical statement and it is mathematical formula is Iz is equal to Ix plus Iy. Now we are going to prove this formula. Iz is equal to Ix plus Iy and it is the proof of principle of perpendicular axes. And this proof will be expressed in similar manner as that of the proof of parallel axes, in which two important steps are: if you want to determine the mi of a body about a given axis, any given axis, then the first step is derive mi about an element, and then from integration we get a mi about that given axis. So 4 points of this proof are consideration, diagram and main mathematical part. So write down the first point, consideration, in which we are going to consider a lamina in xy plane. So our consideration is: consider a lamina in xy plane. Consider a lamina in xy plane with z-axis. Z-axis is perpendicular Z-axis is perpendicular the plane to the plane of lamina. With Z-axis is perpendicular to the plane of the lamina and passing through the origin and passing through the origin or point of intersection, origin or point of intersection, passing through the origin or point of intersection. This is our consideration. Now we are going to represent this consideration in a diagram. Now these are our three axes. This is a Z axis, this is X axis, this is Y, and this is a origin. Now suppose that this is any point P, and at that point we are going to draw perpendiculars AP from on PA on x-axis and PB on y-axis. So here is a perpendicular, and suppose that this distance is r, at which there is a element of mass and dm. So this distance is x and this distance is y. After completing this, then show here a lamina like this. Draw this figure. In this way we complete a second point, means a diagram. After diagram, our next point is the notation. So the notation is about the EMI. So right here, third point is notation, where let Ix, Iy, and Iz. Ix, Iy, and Iz are EMIs of a lamina. Are EMIs of a lamina. Are EMIs of a lamina about an axis, x, y, and z respectively. This is our third point, which is a notation. Now our main point. It is a mathematical expression in which we are going to use first two steps, EMI of element, then EMI of a body. Now in order to determine the EMI of a lamina about x, y, and z axes, suppose that P be the any point in the lamina at a distance r from the origin. So write down, in order to express EMI of lamina, in order to express EMI of a lamina about three axes three axes, AXES, about three axes. Suppose that suppose that suppose that PB suppose that PB any point on the lamina. It is shown in figure. Any point on a lamina at a distance r from origin, at a distance r from origin, at a distance r from origin. Suppose that P be the any point at a distance r from origin, and it is also shown in the figure, already shown in this figure. Now draw perpendiculars. Draw perpendiculars PA and PB. PA and PB on X and Y. On X and Y axes respectively. On X and Y axes respectively. It is also shown in figure. Now therefore mi of a element, therefore mi of element of mass dm about x-axis is the distance of a point P about x-axis is PA square dm is equal to y square dm We know that this is our first step, element, y square dm. Therefore mi of a lamina means body in this case. Therefore mi of a lamina about x axis is, we know that it is denoted by x is equal to integration of y square dm. Suppose that this is equation 1. We know that equation 1 is expressed in two steps by using two steps. First is mi of element, and from integration mi of body or lamina. Similarly mi of a lamina about y and z axes is क्या r z axis is, it is iy is equal to integration of pb square dm is equal to integration of x square dm. This is our equation number 2, and it is also expressed by using these two steps, element and then body. And therefore Iz is equal to integration of OP square dm is equal to integration of r square dm. This is our equation number 3, because OP is equal to r. Now we know that Our next point is use of Pythagoras in the right angle triangle OAP. Therefore, write down from the right angle triangle OAP we get from a right angle triangle we get from this is our next step from right angle triangle we get from a right angle triangle we know that the right angle triangle is OP square is equal to PA square. OP square is equal to PA square plus OA square. PA square plus OA square. And therefore it is equal to R square is equal to PA square means Y square. Y square plus X square. Y square plus X square. We know that this is quite similar like equation 1, 2 and 3, but difference is integration and element of mass dm. So we know that this above equation can be expressed by multiplying dm and integrating. So write down multiplying above equation multiplying above equation by dm and multiplying above equation by dm and integrating we get so the equation becomes integration of r square dm is equal to integration of y square dm is plus integration of x square dm, and therefore using equation 1, 2 and 3 in above equation we get, therefore using equation 1, 2 and 3 in above equations we get Iz is equal to Ix plus Iy. This is our principle of perpendicular axes. Hence the proof. In this way we completed the proof of this principle.